right, so let's go back to precipitation reactions. So precipitation reactions are when the two things react together and they form an insoluble solid. And we're going to learn how to write what's called a molecular equation in this section here. So let's go. So let's go ahead and do a brand new one. So for instance, let's react silver nitrate, which is soluble in water, with something like magnesium iodide, which is also soluble in water. And what we have to do is we have to learn how to predict what the right-hand side will be. In this approach here, we're going to do what's called the double replacement reaction method. And essentially what we're going to do is we're going to swap partners. So underneath, I like to write, and if you've got colored pens, I think it's kind of handy to write the cations and the anions. So the silver is +1. How do you know that? Well, actually, nitrate's -1, and since they cancel out, right, it has to be +1 in comparison. And on the other side, you've got I2. Now, what's interesting with I2, right, is I2, if you find iodine by itself, it actually is diatomic. It is I2. But in here, the 2 is just telling us that we've got not one iodine, we've got 2 iodine ions or iodide ions. And from their location on the periodic table, you know, iodide is I-. So this is what we're going on here. Now, double replacement, what double replacement means is that both of those ions swap partners. So the nitrate trades places with the iodide, and the iodide trades places with the nitrate. So this is what we call double replacement. So both ions swap places. So the nitrate swaps with the iodide swaps with the nitrate. And this is the general rule actually here. So we want to always keep the positives next to the negatives. So when we trade them around, right, the negative has to trade for another negative, right, in order to keep the pairing plus to minus the same. And if we trade negative for positive, we'll get 2 positives and 2 negatives, which is crazy. So now on the other side, here's what I like to do, right? I write the ions underneath. So there's my silver and my magnesium. Okay, they haven't traded, but the iodide is now where the nitrate used to be, and the nitrate is where the iodide used to be. So those are our traded products here. Now, how do you write the formulas? You write the formulas by basically just doing that crisscross method. So we looked at earlier. So you got one of these, and you got one of these, and you got 2 of these, and you got 1 of these. So that allows you to write on the line above, it is AgI, right? We don't write the ones in. And it is Mg. We got 1 of those, but we got 2 nitrates here because we crossed down a 2. And remember, with polyatomic ions, right, when we have more than 1 of them, we put a parentheses around each side, right, and we put the coefficient down below like so. So that is the final product side here. Now you might say, hold on 1 second, right, because you got 2 iodides here, and you got 1 over here. And so we haven't balanced the equation yet. And we balance, remember, by changing coefficients. And I would highly recommend when you do these, right, you do these in 3 kind of steps here. So 1 is you swap ions and find products. Okay, and then 2, you balance. Right? And if you try and do 1 and 2 at the same time, that's okay, but I think it's kind of confusing. And then 3, you find the precipitate, and we'll talk about how to do that here in a second, so that's just for completion. So we balance the equation, and I think the easiest way to balance these, right, is to look at the ions and say, what should we say? There's 1 silver, so it's balanced. There's 1 nitrate. Remember, it's easier to look at the whole polyatomic ion as a unit. And there's 2 nitrates over there. So we balance that by changing coefficients. So we can go ahead and we can put a 1 here. I'm sorry, we can put a 2 here. Oopsie daisy. Okay, that gives us 2 nitrates on each side. But that gives us actually not just 2 nitrates, it gives us 2 silvers. And there's just 1 silver there. So we need to balance it by putting a coefficient. So there's 2 silvers now. And actually, did that mess anything up? Well, now there's 2 iodides. Oh, there's 2 iodides. Perfect. There's 1 magnesium. There's 1 magnesium. So we have done step 2 here. So we have balanced the equation, and we already did step 1. So the very last thing is find the precipitate. And we don't know how to do that. So let's go ahead and move to a new slide, and I'll show you something really cool. So we can do this a number of different ways. One way, we can actually go and do these experiments. We can take every single ionic compound, dissolve it in water, and write down if it dissolves or if it actually just sits at the bottom. And there are several, 10 million or so ionic compounds, so that kind of sucks, to be honest. Or the other way is we can do that. Someone's got to do it, I suppose, and we can look for patterns. And these patterns are drawn up in a table, which we call the solubility rule table. And let me pull the one out of our textbook. Okay, so the way our textbook does it is it lists in table 5.1 everything that is typically soluble. And some things, there are some exceptions. So, for instance, all ammonium compounds are soluble with no exceptions. But if we go down and we look at, say, iodides, all iodides are soluble unless they have silver, mercury, or lead. And all sulfates are soluble unless they have barium, mercury, or lead attached to it. So if you're not on this list, you are considered to be insoluble, unless it's something like water, where water is soluble in water, of course. So we should go ahead and we should try using this list. So let's go ahead and write down a couple of ionic compounds and use the rules. So for instance, if we had something like sodium nitrate, we could ask ourselves, is it soluble or not? So, and I'll give you this table on the exam, by the way. So we go down through the list, and oh, there it is, sodium compounds. They're all soluble with no exceptions. So it's definitely soluble. And actually, if we went on down and we didn't see the sodium thing, we would see nitrates. They're also on the soluble list with no exceptions. And what does that mean? That means that when we see these in a chemical equation, we can write AQ next to it, because that means it's soluble, it is dissolved in water. So if we formed sodium nitrate, then we would write that. I think in our equation we had magnesium nitrate on the right hand side, and I think we also had silver iodide on the right hand side. So we should probably go ahead and figure both of these out. So we can just apply the rules. So magnesium nitrate, we go down through the list. Magnesium, no nitrate, magnesium nitrate, nitrate. Okay, there you go. All nitrates are soluble with no exceptions. So even though we don't find magnesium on the list, we can immediately write magnesium nitrate is soluble, hence AQ. And if we go on down and look at silver iodide, if we go on down, there we go, iodide, and it is generally soluble, with the exception if it contains silver, mercury, or lead. So since silver is right there, that means that the whole thing is not soluble in water, so it is a precipitate. So PPT for short. S just means it is a solid. Almost all ionic compounds, by the way, are solids, and when they dissolve in water, if they dissolve, we will write AQ. So that is our solubility rule list. And just for practice, here's a couple for you to try. And why don't you tell me if you think they're soluble or not? So for instance, calcium phosphate. How about something like lead 2 chloride? Something like barium sulfate? And maybe something like potassium acetate. So there are 4 ionic compounds. So pause the video, use the solubility rule chart, and decide whether each one of these would dissolve or not. Okay, if you've done that, and unpause it, so here we go. So calcium phosphate is our first one. If we look down through the list, there's no mention of calcium or phosphate. So if this is the list of everything that dissolves, if it's not on this list, then it does not dissolve. So we'd write an S for a solid next to it. If we look at something like lead 2 chloride, we can go on down, and when we get to here, we see chloride, and chlorides are always soluble, but the exception is if it has lead, then it falls off the soluble list, so it is insoluble, so we write an S for solid, so it wouldn't dissolve. Now, if we look at, say, something like barium sulfate, so there's no mention of barium or sulfate till we get to here. Sulfate is soluble in general, unless it's paired up with barium, so in that case, then we would write solid next to it. And if you ever had a barium enema or a barium swallow, that's barium sulfate that you've taken there. It is insoluble. And the very last one there is potassium acetate. So if you go on down, potassium compounds, they're always soluble with no exception, so we write AQ. Now, one thing to keep in mind here, so sometimes people kind of get confused and they look down through the list and they say, oh, okay, well, look at lead chloride here. Well, it says chloride dissolve unless it has lead. And so they'll say the chloride is soluble and they'll say the lead is not. But unfortunately, it's all or nothing. It's kind of like being dead, right? You're not partly dead, you're either dead or you're alive. or you're pregnant, right? You're either pregnant or you're not. There's nowhere in between. So you can't have one ion dissolving and one ion not. So in the compound, they're all in it together. So it's either the whole thing is dissolved or the whole thing is not dissolved. So we just apply the S next to the PbCl2 here and not just the Pb. So keep that in mind. So we can now go back to our last double replacement reaction and we can finish it off. So with our solubility rules, right, we said magnesium nitrate is soluble, so we can write AQ next to it. And we said that silver iodide is insoluble, so we'd write an S next to it. And if you like to decorate your equations like I do, you can write a down arrow there just to indicate that it is a precipitate. All right, very good. On to the next video.